Or I should take them by the order you guys submitted.
Yes.
Yeah, the order you submitted? Okay.
Uh-huh.
Okay. Okay, so Sophie and Turner, you are up. Turn your mics and
Yeah.
live stream.
I can share my screen, Turner.
Thank you. I'm gonna pull up the notes.
How do I share my whole screen instead of just the application?
I'm not sure you can do that. Can you?
You
can.
share the whole screen.
When you click on screen, the little thing pops up.
Cool. Got
Click
it.
on screens instead of yeah.
There we go. Can you see the people in the notebook?
Yes.
Okay. Turner, do you want to introduce yourself?
Hey guys, Turner, and our project is titled Duplicate.
Do we just run through our code, or do our presentation first?
You do your presentation first, then the demo.
Dr. Anka, you're echoing.
I do? Okay. I wonder why.
So this is our presentation for Duplicant. So our project Duplicant is an effort to create a handwriting recognition software that takes in images of handwriting from a variety of different users and then is able to compare them against my handwriting. We'd hope to create a model that had 97% accuracy and compare words written in English and lowercase.
And the potential uses that I found most prevalent, or at least right away, were identity verification and protection, which both sort of fall under the fraud category, and those could be both useful uses.
So the packages that we used for this project were NumPy, Sklearn, OpenCV, Pillow, and Matplotlib. OpenCV was just to display the images that we were running through to the user, just for a bit of effect, and so you could see the images.
To install, you need the above listed packages: NumPy, OpenCV, Pillow, Matplotlib, as well as the databases from IM that we'll mention later, and the handwritten ones that Sophie created and imported to Jupyter.
So the data sets we used, we split them into training data and test data. We just split that manually because of when we were running through the, I suppose we could have done either way, but it was just the way that we did it. So training data, S1 and S2, S1 is mine. And on the right-hand side, you can see like in comparison of the two images. So the top one is mine, and then the bottom one is one from the data set that we used.
For this project, we implemented a 4-layer neural network. To do this, we split the neural network into forward and backwards propagation using ReLU and sigmoid functions. And it did the ReLU on the first passing forward, and then sigmoid on the back pass, right?
It was really on the first 3 layers, sorry, not 2. And then on the last layer, it was the sigmoid, and then backward was sigmoid first, and then relu on the last three. So this is just a comparison of the two functions. So they work differently, and like different ones have different successes. But we thought we'd do a combination of both, just from articles that we read and where we were trying to copy, well, not copy our code, but get some of our code ideas from.
Our goal in implementing the neural network was to reduce the cost function, and we almost got our exact goal. We were 0.15 off, I believe.
Something like that. So this is just like a graph. So this prints out in our code, just as like the number of iterations goes through and the number of times that it applies the forward and backward propagation. You can see the cost decreasing. So this is with the learning rate of 0.074. Our aim was to get the cost down to 0.3. Obviously lower than that was ideal. But for some reason, we couldn't really get it lower than this point right here that you can see. It just started to produce errors. I think maybe overfitting and stuff like that might have just started occurring.
And so here we can see that the accuracy, although not reaching 97%, we're both close, being 67 and 80. And this shows not too much overfitting of our trial.
Yeah, so both of the training and test produced similar results. And so when I was doing some research, that kind of said that, you know, there was no overfitting in the model if you can get them both the same. But we did believe that the lack of accuracy probably came from just not having enough data, because we only had about 400 images. And the thing about AI is it's very data driven, and you need lots of data to get a good model.
So for the creation process, Sophie created all of the handwritten words to scan for hers, and then we got the other words that it was comparing against from a data set from IM handwriting words, and this was all done in Python 3 and Jupyter.
So moving forward, a more extensive library of references, so obviously more images to plug through would give us a better accuracy. In addition of what we really wanted to do if we had lots of time was kind of get like an iPad, and so the user could type in some handwriting, and then we could straight away, I could type in some handwriting, we can do a comparison, like live comparison. And then in a forward detection situation, a lockout mechanism could be implemented to stop inputs if the user gets rejected for accuracy several times.
Should we move on to the code?
Yeah, so the second resource here is a course by on Coursera that I helped to, well, we both looked at to try and help understand the code and to create the code. So this is our Jupyter notebook. And I'll just start running the code. So we just wrote pretty much the same things we said just up here, installing the packages. And then this is just our prepared data. So this is just running through the folders, displaying the images to the user, and then putting them into an NumPy array. So as you can see, when I run this next cell, when I'm running the prepared data, we should get our images loading through here, both our test and training data. And then we started defining, oh, sorry, Tony, you can go.
This is the prepared data. To load in the training and test data separately, then we reshape both of our train and test output values to ensure they're in the correct form, and both the train and test inputs into a linear array in order to apply gradient descent on them.
So these are just helper functions, the sigmoid and the relu. So we just defined it in 2 parts just to help make sure that the shape is good for the forward and the backward propagation. And then this is like the bulk of our model is the forward and the backward propagation. So first it's taking in the parameters and then applying the ReLU on the first 3 layers and then sigmoid on the last layer. We did a for loop in order to allow us to adjust with the number of layers and it still work. So this just gave us an opportunity to try and adjust our model and figure out the best model possible.
And the next initializing parameters was the next function that we defined. We used random initialization in hopes to give our model the best chance at finding the minimum of the function.
Oh, oops. And then we had the compute cost function, helper function, and then updating the parameters. So every time that it runs through the forward and backward propagation, it had to update the parameters with the learning rate that we inputted.
So at this point, the model is almost complete, but we need to define a function to predict what our inputs were. We use this function to help us find the accuracy of our model.
And then down here, we tie it all together. So this is where we specify the number of iterations and the learning rate. And so first, the forward propagation is applied, and then we compute the cost, and then the backward propagation, and then we update the parameters. This stuff is just so that you can print out the cost to the user.
And then in trial and error, we found that the model produced best results with the 4-layer network and a learning rate of 0.074. The next cells load in the size of the model, and we want to run in the model to find our optimal parameters. After running our model many times, we found that we could not get our cost down to our desired value, but as mentioned, it wasn't too far off. This also affected the accuracy when we applied the prediction function on both of the sets. And although this is true, both training and test sets produce similar accuracy. So as we mentioned, again, little to no overfitting occurred. And we believe after our research, all we needed was just more input data.
So I'll just let this finish running through. And then so this last cell down here is taking 2 brand new images and then trialing our model on them. So when we get to that, I'll run that. Go. And then click on this. So it's predicted the other's handwriting from the same word of mine and my handwriting. And that is pretty much our project. Does anyone have any questions?
And this is where they tell us they didn't hear a thing.
Quite nice, guys.
All right, so repeat everything you just did.
Quite nice, guys. Do you guys have any questions for them? Yeah, so I think you reach overfitting in there, and maybe you need to play with your 4 layers neural network. Usually it's like 10 layers to achieve really good results.
Okay, I stopped at like 6 layers because I thought that it was getting worse. So maybe if I had tried more, that it would have worked.
Maybe. Yeah, it all depends. But the paper you looked at, it's a bit old. There are newer papers. There are this subject. It's already fixed. It's already established and quite well researched, and results are quite good. So you need just to read the newer paper on it.
Okay.
Yeah, they will give you more insights on how they do it with the neural network. But good work, guys. Very nice. Very, very nice. Anybody else wants to add? No, nobody. Okay. Good guys. You deserve claps. I don't know where they are. Okay, so
If you type colon, it will give you your emote.
yeah, eventually I'll get the hand. Yeah. Yeah, I cannot get it. All right. All right. Good job, guys. Oh, I got the worst one. It's giving me headache. Okay. Okay. Good job, guys. I guess the next pair is Marcelo and Daniel.
Yeah.
Are you guys ready?
Yep.
Okay. So you have the microphone. We
Okay.
will stay quiet until you finish, okay? So we don't have too much echo.
So
Okay.
I'll screen share then, so we don't have to swap back and forth.
Okay. You got the slides on it?
I do.
All right. Cool.
So, fun thing I learned about Linux and Discord: if you try to stream a screen on Ubuntu, it thinks all of your screens are one screen. So I have to do it by application, or you can just see my entire desktop.
Right. So our project is Magic the Gathering stat generation. So you enter some information about yourself, and you get to go ahead and have your stats generated so that you can add yourself as a card. And some people want to have fun with that, but they want to do it in a way that is not unfair. And that's why we came up with the solution. And as you can see, these are custom cards right here. You have Joffrey from Game of Thrones, and you have Darth Vader, who of course aren't part of the real game, but some people want to have. And there it is. The problem was already summarized. You want to do this in a fair manner, and there's Morgan Freeman as a custom card. So what you do is you enter information such as your name and your stats. I'm sorry, and your description, and then it'll automatically generate the stats for you. We'll talk a little about how it does that in a second.
Yeah, but the idea is to make sure that the cards are balanced, so you don't have any problems with cards being ridiculously overpowered. So they're still somewhat playable.
And that is our accuracy rate. So it was pretty high, and we're really happy about that. Originally, the accuracy score was anywhere from 80 to 85%. But afterwards, it went up to 85 to 95 as we added more text onto it. And these are our cards. So, rather than having a long introduction about who we are, we just made cards out of it, which is pretty cool. So Daniel's description, strokes on his keyboard, he can find out what movie you're going to watch next because he's a data analyst. So, and mine is just a software developer. So I like to automate things that could be automated. And I put, I can make a program that makes another program that'll automate things for me.
So I think, is it? I was trying to get to the slide that had the spread out error, but I think it's later. So the technologies we used is Python 3.6, NumPy, Pandas, Scikit, and then another thing called Kiwi. Kiwi is sort of like the CSS of Python UI development. Similar to Tkinter, but it has its own separate language that you can use with it. And the reason why we have OpenCV and GStreamer there are because they're part of the Kiwi dependencies for cameras. So yeah, just that's how our models work. We do pre-processing, and our first Python file pre-processes our data, turns it into pipelines, and then we export it to object files to go to our actual application program. That way we don't have to have our end user training the data.
Yeah, I'd like to add something onto the pre-processing. What we noticed is we had a lot of null values in the rows of the data set. So the data set that we went ahead and picked up were about the cards, statistics. Stats on the cards, the name, description, power level, such as that. But what we noticed was a lot of had no values, or they weren't really what we were looking for in terms of the type of card that we were looking for. Because it's very difficult to predict a certain type of card when you're also matching it to other types of cards, such as a spell card versus a monster card. But in the end, we just actually mixed it all, and it actually improved the accuracy. So that, but yeah, the pre-processing was really getting rid of the rows with the null values.
Yeah. And yeah, this is where we did all of our pre-processing, dropping the empty rows and filtering out the data we actually wanted.
Yeah, Pandas made it really, really easy, because instead of selecting, for example, indexes as the columns, Pandas just allows you to make it the whole table or that data set into a data frame, which is basically, and it allows you to select the columns by their names, by their labels, which was neat. And so after that, we just converted the table that we wanted as a NumPy array, and we just worked from there.
So as we briefly mentioned earlier, we actually made a different classifier for each of the data points we needed, because we need strength for the card, we need health for the card, we need how much mana the card costs, what's the type of the card, and the inputs that the user give is the name of the card and the description. So there's quite a bit of different stuff that we have to get out from our many models. Anything you want to add?
Yeah, it's in the next slide.
Okay.
So what you probably noticed was a pipe. You're like, hey, I haven't seen that before. What is that? Well, pipeline allows you to go ahead and merge multiple models together. It runs the data through a sequence of either classifiers, models, or whatever you want it to be. So that's what a pipeline is. And the models or the classifiers run through were the count vectorizer. Given a description of ordered words, we can convert those into series of numerical feature vectors. Now, the cool thing about sentences is that they have a certain structure to it. Words follow others, such as the position of adjectives and nouns and verbs. And so what a count vectorizer does is look at the general direction of where these words are going to go, depending on the ones that came previously. So that's how we, went ahead and started with analyzing the words themselves. And here's the second thing that is being run through. So after we went ahead and got the general direction of the words, we wanted to decrease the weightage of certain words that are not really important, such as is, a, and the. The reason being is because, well, we want keywords. So we want to check out the general direction of the keywords, and we don't really want to pay much attention to words like is, a, and, because they're so random. They could have anything coming after them. And so, in order to improve accuracy, we just went ahead and decreased the weightage of those words with this right here, the TFIT classifier.
Yeah.
Transformer, sorry. And what it does, can you go back to the previous slide, please?
Yep. Apologies.
So what it does is it takes statistics on the relevance of these words, and then it inverts them. So in the whatever paragraph or sentence you look at, you'll notice that the most common words tend to be these right here. The, is, a, and the most uncommon words tend to be the keywords themselves. So, anything like magic spell or stuff like that. And that's what it does. We just inverted the relevance, and that's how you get keywords popping out. And finally, this is actually the classifier. So, the third one that you saw inside of the pipeline, the SGD classifier. So as it implements regularized linear models with stochastic gradient descent. Yes. It's pretty much like a SVM. So SVM, Daniel, do you remember what it stood for?
Support vector machine. It's similar to the SVM model.
Yes.
However, in this particular data set, it tended to get higher accuracy than when we use the SVM.
Right. Yeah, and those are the three things we use inside of the pipeline. So it's pretty neat that you can go ahead and do that instead of making a bunch of variables and then passing in the previous information onto them. So that's that was a neat part. Oh.
So yeah, this is just I don't know what that was for, but
go back. I can explain it.
Go back. Okay.
Yeah, so this is the test data. Rather than a train test split that you would normally do, I went ahead and went cowboy and just imported another deck and used that as the. So we retrained the model with deck 1, and now we're just going to go ahead and test it with deck 2. It's a bit risky, but I wanted to see whether or not the model would be very accurate. And as it turned out, it kind of was. So it went anywhere from 85 to 95%. And that was really so.
All right. So the ending accuracy we got distributed across our different attributes is this. Highest being our power statistic and the lowest being our mana cost.
Yeah, keep going. Oh, and of course you have the GitHub repository.
And on the right, that's one of the cards we actually generated with the model.
John Cena.
Yes. So just sort of the actual data points that we generated is these two, the typing, and the mana cost up here. This and this is the given to the models. And these are some of the resources we use to build our actual application. We using the MTG JSON renderer, just sort of looked at it and adapted it to make it work with Kivy. The CSV GitHub is where we got our data, and the other things are just Kivy resources for the most part.
All right, now comes the fun part.
Yes, the fun part. So if I pull up, here it goes. All right. Yeah, so as we sort of briefly went over before, we have 3 files. We have our file that generates our model objects, which comes here. This is where Pickle exports them into OBJ files. And then we have our actual application file,
I think you're still on the PowerPoint screen.
Ah, yes, indeed. I'm gonna have to close it and reopen it. Oh no, here we go. Got it. This is just how we're gonna have to do it. Enjoy looking at my entire desktop. So, on the right-hand screen, because unfortunately I can't show you just one screen, is our main file, our application file. And we also have our KV file, which is sort of, again, like a CSS sort of thing, where this is where most of our UI is built from. When you run the main file, it pops up a UI like this. And in our offline mode, we have our different inputs. Someone want to give me a name? Any volunteers for a name for a card?
Go with Shaquille O'Neal or Fluffy.
I can't spell that. I'll do Fluffy. There we go. All right.
I wish we could see this big.
I can make it bigger.
Okay.
Could it be on one monitor?
Yes.
Might not
Even
scale
bigger.
prettily, but we'll see.
So what? Wait, what happened with the
Bigger?
monitor?
Hi there. So I'll just use my bear prop again. Haha. And then if we run it, this is kind of the reason why I wasn't scaling it, but this is what it looks like. And we have a 3-mana red human druid.
Can you make that bigger so we see? It's tiny.
Yeah. Could you switch to
Yeah,
one?
just
Is that possible?
Unfortunately, it doesn't scale very well.
it's okay.
Okay.
Oh, okay. That's good enough.
Well, can you sort of see it? Anyways, anybody have any questions?
What does this mean for the future of burn players?
That's the question.
No, I don't have a good question.
It means we really need to wonder if this will be included in commander decks or not. Anyways,
I have a friend who is into those kind of cards things. The sooner I can get to him, I will, with your permission, of course, I will send him the game and get his feedback. He's actually not only a card player, but he also likes to develop games.
Oh, is it Dr. Ganai?
No. No, it's another person.
well, I think that's it. So.
I just wanted to get his feedback. He actually did put on the market a game called, if I remember, no, I don't remember. Yeah, I don't remember. It's a cards game, and it's selling quite nice.
Yeah.
Here, let me try something. 1 second. What about now?
Yes. Yeah. Woo.
Oh, nice. Super nice.
Ultimate programmer extraordinaire. Fluffy.
Super nice. Super nice. bear and all.
Yes.
I have a nice bear too. Huh?
Questions?
Um,
If y'all want, you can upload a photo of yourself and we can. But we have to choose the description just so we make it.
One other thing. Installation requirements, because I almost forgot to talk about that.
Okay.
The camera add-on for Kiwi requires Linux, so this can only run on Linux. Other than that, there are 2 commands that you have to use, and you can grab everything else from a Anaconda Navigator window.
Yes, and I'm pretty sure it could be with JavaScript. So, if we ever wanted to go, post it in the market, we probably could. It's just maybe a month or so.
Yep.
yeah. So, what exactly is the pipeline?
Well, as I swap screens again. We used the pipeline so that we could put all of our pre-processing and our classifier in one object so that we could import that to our other file. So this is the actual piece of code that's loading the object files. And since they're in the form of a pipeline, we don't have to do any like individual pre-processing on the data we get in. It just does it on its own.
Okay, so it's a strategy in Python. We have mentioned it, I don't remember which, but we mentioned you put things in order, and the moment you build an object like that, it's like you build a class or an object in Java, and you put inside the object, do this at this time, like initialize the object, then do some surgery on the object, then print it out. That's a pipeline. You build up this compact structure, right? So the same is pipeline. Build up a such compact structure where things are done once you immediately just call the pipeline. It just does it by itself. You don't have to redo it. You don't have to reprogram anything. Okay?
Sweet.
Okay, guys, good job. Do you guys have questions for them? So we need to all of us send as a photo and the small description, and you make us cards, right?
Yes. Also
All
a
right.
name for the card, but yes.
Yes,
Right.
cool. And then we get them out as PNG images or JPEG, or what are they?
It comes out as a JPEG.
Yeah, cool. Yes, absolutely. We want all of us to have cards. Very nice. Nice work, guys.
Thank you.
Okay, so next is Christian. Are you ready, Christian?
Yeah.
right.
But my partner's in general right now.
She's here. She just doesn't connect to us.
Yeah. Oh well.
So you want to wait for her?
I can just do it on my own, I guess.
Just ping her. She went to general in place to went to the class. Come to the class.
Oh, then.
Yeah. She goes back there. I wonder if I can grab her. Yeah. I forced her in. Okay, Israt, you have a surprise. You have to be part of the class. Cannot escape anymore. All right, guys, go ahead.
So this is our presentation on illness detection. My name is Christian Henderson, and I am working with. All right, I'm working with Israt Liju. The purpose of our project was to create an algorithm that could predict the likelihood of someone being afflicted by heart disease using their age and their cholesterol level. The technologies that we used were Python and Google Colab. And to install it and run you would download the .ipnyb file and upload the illness.txt file and the utilities file, and then run the program. The data set we used was made it was from Kaggle. We learned that one of our observations was that we kept encountering the same problem with every iteration of the project, that our accuracy was far lower than we had hoped for. And we assumed that was due to our relatively low sample size. We were able to implement most of the major parts that we wanted, but the project currently cannot accept .csv files like we originally intended, and its accuracy is far lower than we wanted. And we wanted to increase the accuracy of the algorithm by a lot and make the graphs look nicer and allow the reading of .csv files rather than a text file. And in the future, we would like to add user-entered data so they could just enter their own data on the program, as well as other quality of life improvements. Those are our references. And this is the program. When you run it, you just click run and it plots the data with the cholesterol level on the Y and age on the X. It makes its predictions and prints out the accuracy, which is, again, far lower than we had originally hoped for due to its low sample size. And then it makes a confusion matrix. And that's if it would load. And that's about it with the project.
Okay, guys, do you have questions for them? Okay, guys, so you didn't tell us what you actually used. What algorithm did you?
Oh, we used naive Bayes algorithm.
I saw a regressor in there.
Yeah, there was logistic regression too.
Okay, you need to tell us all of those, okay?
All right, my bad.
So I'm confused on who did what. Can you go back to presentation or code? I'm confused which part you did, which part Isra did.
I made the program and she made the PowerPoint.
Uh-huh. Okay, guys, do you have questions for them?
Nope.
All right. Good, good. Good. Let's move to the next group. Oh, let me figure out.
Oh, Daniel had a question.
Oh, go ahead, Daniel.
Why did you guys choose the naive bias classifier?
That's the one I just thought would work the best.
And they did?
I mean, its accuracy wasn't as nice as I wanted, so I guess not.
So it's good, but it's not one of the best ones to use. There are better regressors to use, actually. Way better than naive Bayes. Yeah. Did you play with any of the others?
No, we went in thinking we'd use that naive base, but hindsight, we shouldn't have.
Okay. I see a question. Oh, okay. Okay. All right, guys. Thank you for the presentation. Let's go on to next team, which is Danielle and Jimmy. Right? Are you guys ready? And they both run away. Okay, okay. Okay. Okay, guys. Start your presentation. We have one more after you. Okay?
Okay. Wait, two more?
Jimmy,
Yes. Go ahead.
All right.
let's say, Jimmy, you want me to stream my screen?
Oh, I was about to, but okay, all right.
Okay.
It makes
You
it
want me to
easier.
do it?
Yeah, it makes it easier because I'm recording as well.
Okay, that's a good idea. All right, hold on. Let me minimize some things. Hold on. I gotta pull the slideshow up. Forgot that part. Okay. You know what? I'm just gonna leave it in the screen because I don't really. Okay. Give me 1 second.
So, this code that we have, it finally ran today for me, like right before class starts, because it kept having some sort of missing module, and I finally somehow fixed it. I don't know. I just waited an hour or two, and it works. So, I'm not sure why. It went out like that, but
So, all right. So we kind of had a different approach with our project. Instead of trying to solve a problem, well, in a way. So we wanted to learn more about reinforcement algorithms. So we decided to use a tutorial to, I guess, kind of learn more of how the process works. So what we have is a AI bot that essentially plays the pole cart game, where the point of the game is you're supposed to balance a pole on a cart using just left and right inputs.
yeah, you're
So
supposed to keep it balanced, and it's really shaky. So If you once the AI shows it messes up a few times before it gets it kind of right.
So yeah. All right. So what we used was a toolkit called Gem, which is by OpenAI. And basically what they do is they have a bunch of reinforcement algorithms that they have in environments so that the AI can learn how to adapt to whatever environment that your code renders. And it's actually pretty cool and simple to learn how to use. So before we show you, we have to
Yeah.
well, first,
A little comment right there. Installing the correct module and library was a pain. That's definitely why I couldn't get the program to run for the longest amount of time.
yeah, it took forever.
Right below this, the next slide. What was it? It's all the imports that I had to install. Like I couldn't get most of it to install correctly, and it was really difficult.
Yeah, and I had to install something on for my graphics card and stuff. It was a lot. But yeah, so we had to import Gem and Random for the actual directions, NumPy and Keras because of the what's it called? Neural network. So this is where we have the variables initialized. So basically what we're saying is that the goal is that the computer only takes like 500 actions, but still get at least a score of 60 on the game, and they have to run through this game 10,000 times. And that's just for training it and whatnot. And then after that, we had to prepare the model. Oh, we had the sorry. We had to do the training. We had to create the training data for the model so that basically it loops for the number of times that we had set earlier, and then like every game that it makes that hits the requirements and then like has that score, it like stores that, and then also stores the score that it got for the actual training part. And it's the part where the neural network gets made. Yeah, and then this is the part where the model gets trained using our training data, and then this is where all the fun happens, where it actually the game and plays it 20 times, because honestly, this is the biggest resource hog I've ever dealt with on my PC. So it's going to run through 20 games and then just print the score for each time and like the average amount of it prints the score for each time, and then for every time it plays, how on average how many times did it go left and how many times did it go right. So
to balance the poll.
Yeah, to balance the poll, because poll on the card, gotta balance the poll on the card. So now we run our code. So when we ran our code, the training data shows the training data from all 10,000 games. Obviously, that's not 10,000 entries. And everything is, of course, 60 and above. Then this is the part where the model's being created. And this is where the GPU goes. Well, this is where your memory goes into full power. Yeah, because originally I was doing we were doing an Atari game, and then my computer was like freaking out, and then ended up running out of RAM, and I couldn't even record anything because the video card recording thing would stop working, and yeah, it was complicated. It was terrible. That's why we're using a really crappy game, or else it would have been like Asteroids or something. Sorry, I'm not rich with a cool computer. This is all the scores it got for every game that it played. So on average, it had a score of 190.5, and it went to the right and left about like 50-50. And this is it running it. And since and that's how much RAM it's using, plus the video card's RAM. We're just a game of a stick on a cart. So yeah, and then
the next one should be a video of it, but I guess we could just run it instead of showing you a video of
it. Yeah, I can totally run it. All right, let's run it. All right, let's do this. Hold on, my bad. I don't want. Okay, all right. So So here it is. So I'm just going to run this loveliness. I wonder if I can. There we go. All right, cool. Okay, so I'm gonna zoom in a little bit so y'all can see it running and going through all its funness. Okay, so it was kind of quick, but at the top you see the training data right here, and then here it is like learning stuff, and then now there it goes playing the game, balancing the pole on the cart. It's doing really crappy this time. Okay. Wow. Okay, so I might have to up the number of games it plays because it's really doing really crappy right now.
Wow.
Yeah, like yesterday did way better. Actually, you know what? I'm gonna try it. Okay, so I'm gonna run it 20,000 times and let's see how it goes this time because that was really crappy. That wasn't impressive at all. Kind of upset. All right, let's see. So this might take a tad bit longer since it's doubling the number of times. Okay, it didn't take as long. Okay, cool. All right. Okay, it's a little bit longer this time.
We might have to cut it short because someone else is after us.
Okay. Yeah, so yeah, it's playing better this time. So yeah, after I upped the number of games that it played for the training data, it's now playing better. So yeah, that's our presentation. Us trying to figure out how reinforcement works. Any questions? Thank you. Oh my god.
Yeah, that's cool. I did hope that we originally we wanted to have it like play like games like Portal. I believe I remember Daniel talking about that, having it play like a 3D game. But,
Yeah, but they have so much extra. There's so many packages.
There's so much things to install.
Yeah, it was terrible. But yeah. Huh, cool.
So yeah, pretty nice. Okay, pretty nice. So it's based on TensorFlow, right?
Yeah.
Good, good. What else did you use in that? So you mentioned reinforcement learning.
Yeah.
Yes, reinforcement learning. Yes.
Which one are you? Do you know?
So what is the word? Okay, so Gym has like its own algorithm that it uses for its environments. So I didn't really go deep into learning which exact one it was using.
Mm-hmm.
Yeah, so
All right. So who's next group?
all right, let's go. Next one. All right.
Kind of nice, guys. You should go a bit deeper into their learning algorithm.
Okay.
Definitely.
Feedback. Other than that, pretty nice project.
Thank you.
Hmm?
All right, back to mute.
Yeah.
Okay, Anne, your turn. You cannot be quiet anymore.
Okay, so you guys can hear me?
Yes.
Okay, I'm gonna share the screen. You guys can see my screen now?
Yes.
Yep.
Okay, so my project is about cuisine checker, and I'm the only one in this team. So my abstract is using artificial intelligence to predict cuisines based on the ingredients fed into the system. So the technology I used is NumPy, JSON, Pandas, TF-IDF, the one the other group, Marcelo's and Daniel's group was using. And I'm using CSR metrics, PCA, K-means for clustering, and Matplotlib to plot. So how to install? So I did this in Jupyter Notebook, and to run this project, you'll have to have NumPy, JSON, Pandas, SciPy, sklearn, and Matplotlib. And also need the Jupyter Notebook and the file. So the data is stored in JSON format, and it includes a recipe ID, the type of the cuisine, and the list of each ingredient in the recipe. And I got the dataset from Kaggle, which is provided by Emily. So mainly I used these two techniques, term frequency, inverse document frequency, and the PCA, principal component analysis. So as the other group said, term frequency, inverse document frequency, this technique is used to get the least common word used. So if you look into the recipe, so for example, this, so the most commonly used ingredient would be salt. Like in all other cuisines too, we use salt. So I need to get the not much used ingredients so as to know which cuisine it belongs to. And that's the reason why I chose TF-IDF technique. And PCA, principal component analysis, this is a technique, a dimensionality reduction technique, which identifies patterns and correlation in the data set so that it can be transformed into a data set which have very low dimension without loss of any important information in the data set. So I'm having a huge JSON file, and a lot of ingredients, and that's the reason why I used PCA. Okay, to-do list. So I wasn't actually able to create a final product, which I thought I would. But I did have the functionality set up, like with the training data, but didn't get to do it with the classifier so that I can use the test data and predict the accuracy and predict and see the accuracy and all. And then I think later I should add a feature where the model also can find nearest substitutes for the ingredients. Okay, so any questions so far? Any questions? No? I'll take that as a no. Okay, let me go into my code. Okay. So I first imported NumPy. Okay. I imported NumPy and JSON first, and then loaded the train.json file, and then I started with TF-IDF technique, where I created a dictionary and arrays for cuisines and ingredients. So in order to run TF-IDF, I need to do I did it in 2 steps. So first I created the dictionary and took all the so you see in the so there are, I'll show you the JSON file. Hold on. So this is my train.json. So you see a lot of cuisines and ingredients. Cuisine and ingredients. So what I'm gonna do is I take cuisine, say Indian, and I'm gonna add ingredients of all all the IDs which have the cuisine named Indian. So all these ingredients are going to go under the cuisine name Indian. So sorry. So that's what I'm doing here. I'm gonna have the cuisine name and then gonna add all the ingredients that comes under that cuisine. And then I'll start counting the terms, the number of terms, number of ingredients in each cuisines. So that's what I do here. And then I use TF-IDF technique, term frequency, inverse document frequency technique. And there I generate the TF-IDF metric using this function. So I used CSR metrics because as I have a lot of rows compared to columns, and that's the reason why I use CSR metrics, as it has faster row slicing. And okay, PCA. So as it comes out in a very complicated dimension, so why I use PCA is because a high dimension data, as it is complex to process, I had to increase. I had to decrease the dimension in order to decrease the computation time and make data processing much easier. So I reduced it to 2 dimensions. And then in order to visualize, I use k-means to cluster and matplotlib to plot the data. So here we see that southern US and Spanish resides. So Spanish and southern US are we see it, they are in different clusters, but they are thought to be closely related, but it's not. And also Greek and Moroccan cuisines are also considered different, but actually they are similar. So this is what I found out. Any questions so far?
It's very nice, Anne.
Thank you.
Is that it?
Yeah.
Yeah. Okay. So it's very nice, and the fact that methods TF-IDF. TF-IDF it's used in information retrieval. Is basically all those algorithms that make you recommendations, they are texts of data from the
Yeah,
internet. Okay.
Yeah, as I was using JSON, I
Yeah,
used.
all the documents, they build the TF-IDF, and based on those scores for each term, then they reduce them by using PCA. So
Yeah.
it's a straightforward method. It's not that new, but it works wonders. And the ones that have the higher score are getting to be recommended to you guys. So that's how those recommendations work. In addition to pre-known cluster data, this is for raw data, and it's done every night actually. So it's very nice to that.
Yeah, it came out good. If you look like Japanese, Chinese, Korean,
Mhm.
they're all similar.
I think build up more and do money out of it. Basically, right now, people need to build some food, right, to cook, and it depends on what is so they might not have all the ingredients.
Yeah.
This is a very good subject to build upon. Okay.
Yeah. Okay. Thank you, everyone.
Have any feedback for her? Any questions? She's ready to run away, you know.
I'm not. No. No questions.
Quickly, run away. Run away while you can.
Yeah, it was nice, Anne.
Okay, thank you.
I agree with Turner. It was nice. Good job. Good job, everyone. So what we have now, reminder, is that so 5/5/2020, that is on Tuesday at 9 a.m. Final exam. Okay. So I decided to make it simple. I like your projects. So because you put a lot of learning, extra learning in those projects, and all of you kind of went outside and learned little things that are new, not only libraries, Python, and had fun with those, but you also learn new techniques like algorithms, right? So because of that, we will have only the quiz part. So there is no practical. This was your practical. Okay? So be on time because the quiz might go for only half an hour. So be on time and don't miss it.
So how many questions are there?
Not that many questions, but the exam is comprehensive. So prepare well, okay? Take a
Is
look
it
at what you had for midterm as well. There is a review of the subjects material that I put on.
Is the
Daniel,
exam
you had
open
a
book?
question? Huh?
Is the exam open book?
If you want it open book, yes, it's open. I'm not sure you want it open book.
Yeah, why not?
Okay, and if you want it open book, it's open book for you. For the rest, they don't want it, so.
Oh yeah, they don't want it.
No, they don't say anything. They are just so. Okay. Okay, guys. So it's open book, but it's gonna be time restricted. Okay.
Okay.
I don't know if it's half an hour or an hour, but it's not gonna be an hour. So come on time. And is there anything else you want to ask me?
Oh boy. Yes.
No making any 2 hours. No way.
The assignment that's due today, can you push it out one day?
What assignment is that?
I don't remember the name of it off the top of my head. It's the I think it's the Keras one, but there is an assignment that's due tonight.
Oh, I see. Okay. Sure. Do you guys want it? I can push it as late as Saturday, so 2 days.
Woo!
That would be
Okay.
wonderful.
Okay. So give me 1 minute. Okay, Saturday it is, but no later than that. I need to start grading. Okay.
Okay.
So make sure you push. Speaking of that, you have that bonus points in there. Make sure you put all your extra activities you did. Coming Tuesday, I'm closing any submission because I need to grade. Okay. So turning everything by Tuesday night. After that, nothing. Also, I put bonus points for you guys to take a survey for the class. The survey is on the 12th. So go ahead and spend like, I don't know, 10, 15 minutes and take that survey. There is another survey given by the school, but you have to provide me the proof of it. So take a screenshot or the email you receive and stick it into a D12 folder. I put a D12 folder there. Okay? So do all of those things. They're simple things, but you need to have them done by Tuesday night. Everything. Absolutely everything, because I need to grade. I need to turn on the grades on Friday morning at 8 a.m. So I have basically 2 days of grading for all my classes, okay? So do all the stuff you need to do. I can open them for you if you tell me, not a problem, but by Tuesday night, everything is in. Okay, guys. If you have questions for me, stay. Otherwise, have a nice weekend. Good job today. I like the project. Fluffy, you sent me the recording, right? And that's it. Stay safe and happy. And the semester is almost over. I can't believe this is almost the last time we talk to each other. Yeah. All right, guys.
All right. See you.
See you.
See you on
Bye.
Tuesday.